Okay.
This meeting is being recorded.
Okay. Yes, welcome everybody to our special topic, CS181, Computing for Languages today. Let's see, last time we talked about the whisper.cpp, a lot of background information, and then we started talking about the context-free grammar stuff. Okay, it looks like the screen over there is getting a little bit fuzzy again. Is this readable to people still? Kinda. Maybe we'll make it one larger to help with the fuzziness. But yeah, your homework related to whispers.cpp. My hope is that for most people it'll be fairly easy, straightforward. The grammar stuff that you have to change and write, not too hard. I think the hardest part's going to be just dealing with the different build system. If you haven't used C, C++ stuff before, you'll run into potentially weird, different sort of error messages than you've seen before, and that just takes some getting used to. But this, again, whisper.cpp, llama.cpp, super famous programs in the LLM world, can do a lot of things that nothing else can right now. So important to be able to use and figure out their documentation. Any questions about anything we talked about last time or the homework? Yeah, Ron.
Yeah, what is like, so when something says it's in C/C++, like what parts of it are, do we know which parts of it are written in C?
Yeah, so here I have C/C++. There's an underlying library called GGML. GG stands for Georgy Jerinov. It's just that Bulgarian guy's initials, ML for machine learning. He happened to be writing this library as a fun side project when llama.cpp when Facebook released Llama at a year ago, and managed to convert that fun side project into this giant now like pillar of the LLM community. That project is written just in C, that library stuff. The reason for doing it in C is usually the easiest language to make interface with other programming languages. So Python, for example, vast majority of like high performance Python libraries, if you've used say like NumPy or scikit-learn or pandas or lots of other things, those are all written in C, and then they have Python bindings, which make them available in Python. C is very easy to do that with, so very common for like back-end high-performance libraries to be written in C. C++ has some more features that's convenient to be programming in. As an example, like Python classes, something like that exists in C++, does not exist inside of C. Those extra features, though, are what make it harder to interface with other programming languages. And so the library is typically not written in C++, the library part written in C, and then the front end part, the whisper.cpp itself, written in C++, but this GGML, like backend library, written in C. Did that answer your question?
Yeah.
Cool. Yeah, good question. Any other questions about anything? Yes.
When it's like in the homework, when on the number 5 and stuff, it says like run command and like show that the command is registered. How do we know that the command is registered?
Yeah, so it should output to the screen, like into your terminal, all the things that you say that it recognizes. And so I think in their like example video, he does like turn on the lights, and it outputs turn on the lights in there. And you should be able to tell your computer to kill all humans, and it will output the command kill all humans.
So if it just says like command kill all humans, that's like the
Exactly. Yeah. And then the way that you would actually use this is that you would have another, like this would be linked to another program, probably using output redirection if you've seen that before, where the commands from whisper.cpp are sent to that other program that actually processes them, turning on the lights or killing all the humans, whatever the command may be. So you're not doing that processing part, you're just recognizing the text, finding this new command. Good questions. Any other questions about the homework or anything we've done so far? Okay, then we're going to, and we started last time talking about your next homeworks. Again, there's going to be somewhere between 2 to 4 homework assignments, depending on how I decide to split things up. I still haven't fully decided. But we'll talk more about these example.py files today, which will, again, give you more familiarity with the writing of these context-free grammars, which will help in this whisper.cpp stuff a little bit, but it's really focused more on these other homeworks where you'll actually be implementing a series of programming languages that are increasingly more complicated. My guess is that we'll probably finish there's 4 examples here, we'll probably finish those examples today and start talking also about some of this other stuff that I have listed here in background and connecting this to some of the power or capabilities of these large language models and things that they can or can't do. So example star.py, there's 4 of these. I have 2 terminal windows opened right now into my topic 6 grammar folder where I've downloaded this, or where I wrote it, where you all have downloaded the files for this course. And in here, there's these example 0, 1, 2, and 3.py that we're going over. Do vim star.py-p to open these up. Again, in Vim, I have these 4 tabs over here, and I'm just switching through them like this. We started talking about example 0.py last time, seeing some formal-ish definitions here. Again, we're sort of speed running 2 semesters of a CS curriculum right here. So I'm not going over the formal definitions of things, but just trying to get you the right vibes of how to think about these things for when you see them. And we talked first about regular languages, that regular languages correspond to things that you can do in regular expressions. This is one of the standard examples of a regular language where you have some string like this that is repeated 1 or more times. The plus here indicating 1 or more times, A, B 1 or more times. And in regular expressions, in order to match the beginning of the string, here we have the up caret and the $sign over here for the end of the string. So these 3 things right here contained in the language because they have A, B 1 or more times and nothing else inside of them. AC right here, not in the language, BA not in the language, and BABA right here, not in the language. Regular expressions, notoriously very hard to read and understand regular expression that somebody else has written. And so it's very common, even for regular languages, to write things out in this grammar form that we started talking about last time. And the grammar has many synonyms that you'll see people use to talk about this word grammar. Most common of them are Backus-Naur form or extended Backus-Naur form. You will see, for example, in the whisper.cpp documentation, they talk about, I don't think they even use the word grammar, they just talk about EB and F all over the place. But if you see EB and F or B and F, then you should think that's the same thing as the grammar over here. The syntax, slightly different, like in whisper.cpp, I think it was like a : equals or something like that. But the ideas are all the same. And in the grammar, so far we've only seen a handful of very simple grammars. We'll see some more complicated ones today, but to the left-hand side of this colon, this is the name of the rule. And on the right-hand side, this is what the rule is allowed to match. The vertical bar here, again, you can think of it as an OR operation, that you do the thing on the left or the thing on the right. The technical name for it is the alternation operator, that you can alternate between doing either one of these 2 things. And here, this grammar, what it's saying is that we either match the string AB or we match the string AB followed by this other production rule right here, start. And so there's a little recursive definition going on here where we're allowed to substitute start in right here, which means that we can match AB again, or do this other rule again, and this allows us to match AB one or more times. So this grammar right here is equivalent to this regular expression up here, but maybe a little bit easier to read. There's a little bit more like built-in documentation about things with the names of these production rules. The actual language that this recognizes is exactly the same. So AB, 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 however many ABs you want. But if you have other letters inside of there, like C, or have them in the wrong order, it's not in the language. One of the things that, I forget if we explicitly mentioned this last time, but in the regular languages, I'll do import re, again, RE here, built into Python. And let's copy and paste some of these lines. I'm going to take away my numbers here to make it easier to copy and paste. For the RE library built into Python, if you have a match, if something is in the language, you get a match, what's called a match object out that contains all the information about where that's found in the string and what the actual match is. If you don't get a match like this, then you get none returned, which the REPL doesn't display at all. But for the grammar down here, you're gonna have to do an import Lark. Lark not built into Python, something that you have to pip install. Copy those. When something is in fact matched by the grammar, we get this tree representation out down here. We'll visualize these trees in a little bit. These trees are very important. But if something does not match, then you get a exception thrown. And that exception describes what the why it doesn't match. These exceptions right here might look somewhat familiar to you from the RASP language. A lot of vague-ish, if you're not familiar, confusing error messages in RASP, but they come from the grammar parsing like this and exactly how the grammar is written. But the key thing when using Lark here is that if it's not in the language, then you get an actual exception compared to regular expressions. Okay, yeah, so grammars can do everything that regular expressions can do, so they are strictly more powerful. They can also do things that regular expressions cannot do. The key example here is if your recursion or your patterns that you're calling, your other rules are inside of two literals like this, then you get a what's called a context-free language that is not a regular language. So here, this language matches a very similar language to the one above, that it's A followed by B, but the A's all come together and then the B's afterwards. And we have to have the exact same number of A's and B's. Not in the language right here because there's not enough B's, not in the language right here because we have a C in the middle, and so on. And then, so this is one of those like stereotypical, prototypical context-free languages that if you have to think of a language that is context-free, that is not regular, this is one of the go-tos. The other go-to language is the deep language, where the A is replaced by parentheses and the B replaced by closing parentheses. And then your recursive rule right here, we have a plus right here, allowing us to do it one or more times, one or more recursions. And that recursive one or more allows us to have parentheses that are sort of right next to each other like this. So this is one application of that recursive rule right here. This is the second application of it. And then the outer parentheses right here. And the balanced parentheses, again, another stereotypical context-free language. These two strings right here do not have balanced parentheses, and so they are not in the language. Let's all review what we talked about last time. Any questions about any of that?
What is there more to the definition of a context-free language?
So the question is exactly what's the difference between the context-free and regular language. So here the recursion. So both of these two grammars are recursive, that they both have this start right here that can be recursively applied. This is what's called left recursive or tail recursive. It turns out that this is much easier to implement to match than something like this, where the recursion happens in the middle of two separate things. So it's the fact that this is this recursive rule right here application is in the middle of two separate things, which is causing it to be context-free and not regular. Yeah, again, one of the things that happens in those like 2 semester long courses is that you spend probably like 4 weeks each fully formalizing each of these regular languages versus context-free languages, and how do you actually prove that something's regular or context-free. And we're skipping all of that, getting just to the intuition that if your recursion happens in the middle of things, then you're context-free and not regular. But if your recursion happens only on one side, then you are regular. Good question. Any other questions so far? Yeah.
This deep language, what is parentheses? Can you go over this plus again? Because you said that you can have, so when you do it with plus, you can add the left one and have it as you want the right. Repeat it.
Yeah, so this plus here, so Lark's grammar allows the use of regular expression looking things inside of the grammar itself. So this plus here is similar to the plus in regular expression, that it means the thing on the left happens 1 or more times. So here, this start, we're allowed to substitute start here 1 or more times into this rule here. And so this very first application of the rule right here, this parentheses right here, only does this version of the rule right here, the left-hand side, no recursion going on. I'm going to make another one right in the middle where we have like this. And what's going on in this is that start does not match 2 parentheses. And so it cannot pick this left-hand side of the rule right here. And so instead, it tries this right-hand side of the alternation operator. This left parenthesis right here matches this left parenthesis right here on the leftmost side of the string. This right parenthesis right here matches this right parenthesis here on the rightmost side of the string. And then the recursion right here happens with everything that's in the middle. In this case, it's going to try to apply the start rule here once, and that matches this like this, and we get the parentheses right here. The next example down here that I was originally example number 2, this parenthesis right here is matching this parenthesis right here matching this parenthesis, and when I had start plus, that allows me not to do the recursion just once, but twice right next to each other. And so one recursion is for the left parentheses right here, and the second recursion is for this set of parentheses right there.
So you just concatenate like the start plus as many times in that one iteration.
Exactly. So this plus is saying that you can concatenate that as many times as you want.
But if there's no plus here.
Exactly. So if we took away this plus right here, if we had that as our grammar, then this would be in the language, but this right here would not be in the language anymore.
So the only language would be like parentheses, like would let all of one side of the plus.
Exactly. And so without that plus right there, this language right here is essentially the same as this language right here, just A's for open parentheses, B for closed parentheses. Let's see, so Deek language, another very standard example, the Deek 2 language, where we have 2 different types of parentheses, opening parentheses and say square brackets. These look basically the same. The rules are the same, just replacing parentheses with square brackets. And now the production rules ensure that anytime there is a open parenthesis, the closing parenthesis has the same type. So this in the language, not in the language down here, because even though we have an opening parenthesis and a closing parenthesis thing over here, they're different types, and so it's not going to match. the main takeaway from this example 0 set of notes is just getting some sense of the power of these grammars, and that they are more powerful than regular expressions, and that these, and in particular, this sort of like balancing parentheses, if you ever need to do something like that, that's what grammars are for, and you can't do that with regular expressions. The next set of examples will actually dive a little bit more detailed into these trees and the output of the parsing, and get a better sense of how the parsing actually works. Any other questions on the example 0 notes here? Yeah.
Exceptions raised when something doesn't match the grammar rule.
Correct.
Is that true of the other languages too? Like what comes up in the other versions when something is matching?
When you say other versions, I'm not sure what you mean.
Like with the language or like the other examples that we're using.
Okay, I see the question. So yeah, I showed an example here of in this first language right here, what happens when we don't match the language. But the question is, what happens in the other examples down here? And the answer is that it's the same thing. That Lark here is not the name of the language. Lark is the Python library that we're using to process these languages. And so if I copy that grammar right there, and then copy, say, like these first lines. This one is in the language, so we get this tree object as output. Similarly, this one right here is in the language, so we get a larger tree object as output. This one right here, not in the language, and so we get one of these exceptions raised. So the important distinction here that Lark is the Python library that processes context-free grammars. There are other Python libraries that also process context-free grammars, and they have slightly different behaviors about things, but they can all support, for example, the deep language here, or the A to the N, B to the N language here. Did that answer your question? Okay, let's go into example 1 over here, and there's a handful of things for us to talk about in this example. The first thing is that this is a much more non-trivial example of a context-free language, and it is sort of like the first real interesting prototypical example of a context-free language. This is the language, or the grammar for the language of all arithmetic expressions. So all of these sort of like math expressions that you might want to do, these are context-free. The language of mathematical expressions is context-free, and it is not regular. So in particular, there is no regular expression that you can write that will check whether a mathematical expression is like a meaningful expression or not. There's a lot of steps in here for us to walk through about what's going on. Let's see, I'm gonna adjust my screen so we can fit it all once here. There we go. And in order to do this, I'm gonna leave Python, come up here and go into example 1.py like this. So I have my grammar is already loaded inside of Python like this. And this parser variable already exists, and this tree variable right here, let's go ahead and define this tree variable. And so a number by itself, we can see that this is in fact contained in the language because we did not get a parsing error. Let's go ahead and just try this one down here. We'll do this one here since it's on one line. We can verify that that is in the language. We did not get a parsing error, but if I say modify this so we have a times right here without a 5 at the end, we will get a parsing error. This is not a valid arithmetic expression. In order to understand this grammar up here, we're going to take a detailed look at these tree variables down here and try to understand these trees. So these, all these trees are generated by a function parser.parse, and this function creates what's called a parse tree. So these tree variables This output down here is what's called a parse tree, which contains all of the information from the string up here just in an easier to access form. You'll also see people use the phrase abstract syntax tree, which in a compiler world is a simplified version of a parse tree. But for our purposes, a parse tree, abstract syntax tree will be the same. And things like whisper.cpp will use those two phrases interchangeably. In order to visualize these parse trees, Python has, or Lark has several options for us. So one is just printing the tree value directly. So that's what we've been doing previously when I've been typing it into Python. Whether you use the print or not print in the REPL, it'll show you the tree down here. This is like the least useful way of visualizing it though. The most useful is actually generating an image of the tree. And so let's go ahead and do that. I'm going to copy this line right here over to here. And so this function lark.tree.pydout.tree.ping will create this from this tree variable, actually draw a tree that we can look at and see what's going on, and it'll put it in this test.png file. I'll come over here so we can take a look at test.png, and this is what the actual output of that tree is. I originally, so I started us off here with one of the more complicated examples, just so that you can in fact see that it is a tree. It looks like a tree. We have a root over here. There's some branches and some leaves, so it looks like a tree. But in order to actually understand this tree, we're going to go back to a simpler example and work through these examples here from top to bottom, going through, starting with the simplest and then getting down to the more complicated down here. So I'm going to, again, line 25 here, run this. The simplest like possible expression just contains a number right here. And then let's take a look at the corresponding tree. We're going to take a look at that tree and the grammar at the same time to see how the tree and the grammar relate to each other. So that'll require me shuffling my screens here for a second. There we go. And refresh that. Maybe before I start going over this, just reminder, what did I do? So we're looking on the right-hand side over here. This is the tree of this tree right here visualized as an image. And this is like the simplest possible expression in this language. Any questions about where I'm at right now, what we're looking at? Okay. So the leaves of these trees all correspond to what are called terminals in the grammar. And a terminal is either a string like this that is inside of a production rule by itself. These are sometimes called anonymous terminals because they don't have a name associated with them. Or terminals are in Lark things that are in all uppercase. A production rule that is in all uppercase is also a terminal. And this type of production rule cannot have any like alternation or any recursive applications inside of it. It can only have a single string or a single regular expression. In this case, I have a regular expression right here. In Lark, the syntax for regular expressions is that they are contained between two slashes like this. And then the contents are the same standard regular expression syntax that the RE library supports. Under the hood, Lark actually uses Python's RE library for regular expressions. What this regular expression right here is saying is that we have first, a number can contain a negative sign. The question mark right here means that the thing previously either may or may not exist in the string. It doesn't have to exist, but it is allowed to exist. So a number is allowed to have a negative sign. And then here in square brackets, this is a range of numbers. Any number between 0 and 9 is allowed to appear, and it can appear, must appear at least once, can appear as many times as we want. So in this case, the string 1, 2, 3 right here matches this terminal number. And on the leaf node, the only leaf of our tree over here is this white node over here. leafs in abstract syntax trees or parse trees, often called tokens. And so this token is a number type token, and it contains the string 1, 2, 3. So this number, anytime you have something in all uppercase, that is a terminal or a leaf node in the corresponding abstract syntax tree. And here I've used a regular expression to define what can match a number. So this regular expression here as another example can match every integer, but will not match fractional numbers, cannot match floating point numbers because there's no decimal place allowed. And then in order to get these other nodes up here, somehow we have to draw a line between the number and the start terminal up here. That the start is always going to be the root of the node in Lark. And in order to make this true, we have to get from this number rule up to this start rule. The way that happens is that the number right here is one of the options of what an atom can be. And so here, this next node right here is atom. And then an atom is one of the options of what product can be. Product is one of the options of what sum can be. And sum is the only thing that start up here can be. So we get from token to atom to product to sum to start. Every one of these intermediate nodes in the parse tree over here corresponds to one of these production rules over here. And again, the terminal over here, the leaf node, the token, corresponds to the all capital terminal production rule down here. Any questions about that? It'll be maybe a little bit more interesting here when we see more interesting strings. Okay, I'm going to take this next rule right here, 1, 2, 3 plus 4, come over here and so I'll define it right here and then redraw that tree, come back over here, refresh the picture. And so now this is my new tree over here. Here we have 2 terminal nodes and 2 leaf nodes, 2 tokens inside of our tree. They correspond again to 2 different numbers that were matched. The one number being matched right here, another number being matched right here. And these numbers, again, they're only found in this grammar as a sort of child of atom right here. And so the number tokens right here always followed by atom over here. And then atom always contained inside of product somehow. So atom, then product. And then the interesting part here happens with the addition operator right here. Product is contained inside of sum in 2 different ways here. This product right here goes directly to sum. So this top branch over here, we have product to sum, is this one right here. I know that it's this one right here because this has only one branch allowed from it, the product branch, sum down to product. But this one right here, we have sum and then plus and then product. Each one of these 2, we have 2 rules right here, sum and product. So this root sum, this sum right here corresponds to this. And then the children of the node right here, these 2 children, sum and product, correspond to the rules inside of this particular branch right here. That this sum corresponds to this node right here, and this product corresponds to this node right here. This particular rule was chosen because this plus had to be matched. This plus had to be matched right here. And so that's why this rule was chosen. And then sum here, sum inside of start. So sum is a child of start right there. Technically, so again, last time we talked a little bit, and I used a little bit of the language of imperative language about thinking about like the ways that a parser might choose to match a particular string. And the way one of the verbs I used was like consuming parentheses or consuming tokens. Technically, the way these context-free grammars are defined is that if there exists any sort of parse tree like this that can be drawn that matches the corresponding grammar, then it is contained in the language. So it's not an imperative description of how you mechanically go about doing something. how you mechanically go about constructing this tree or determining whether something's in the language or not. There is no like imperative definition of that. It's a declarative definition of just if you can construct a tree like this from a particular string where the terminal nodes down here match the terminals over here, and you can follow up a path over here using these different production rules, then it is contained in the language. So understanding the relationship between these trees and these grammars is important. This is so this is more interesting rule than this one right here. Any questions about what's going on with this rule? This mostly makes sense to people? I see a lot of blank stares. I don't know if this is not making sense or too obvious. Repeat the explanation of the tree? Yeah. Sure. So the trees over here in these leaf nodes, these white tokens, these correspond to the terminal, what are called terminal rules in the grammar. And these are going to be the in all uppercase inside of Lark. The thing that makes something a terminal, or what makes it different than these other rules, is there can be no recursion, no like calling out to other rules, and no complicated things like alternation inside of them. It just has to have like a string or a regular expression. So these two terminals right here, 1, 2, 3, and 4, 1, 2, 3, and 4 match the 1, 2, 3, and the 4 right here. And then in order to actually create the grammar here, we start from the terminals that we've just matched right here. We've started from the 1, 2, 3, and the 4. We matched that both of these two things, they must be this number terminal. And then we walk up the root over here until we can somehow get, we walk up from the number here up to the start over here, trying to match our rules until we have constructed a tree where start is at the root. In this case, we have number. The only place that number appears is after Adam, is one of the options, one of the alternations inside of Adam. And so for both of our tokens, Adam is what immediately comes above the token itself. Adam is immediately above or is a child of product right here. Adam, a child of product. So this rule goes over to product. And then the interesting thing that's happening right here is the sum rule that we're choosing. This rule right here, sum to product. Sum right here has only one child of product in this line right here. So sum to product, sum to product. There's only one child from this green sum to this blue product. So I know that it must have chosen this rule right here, this option of the alternation. And then anytime we have two different production rules right here inside of our expression, sum and product right here, because there's two rules, there's going to be a branch in the tree over here. This sum right here corresponds to this root right here, this source of the branch. And then this sum is one of the children, that's this child right here. This product is this child right here. And then the plus sort of consumes corresponds to this plus right here. So this 1, 2, 3 got consumed by this number terminal. This plus corresponds to this plus, and this 4 corresponds to, again, the number terminal. And then the sum itself, going back to the sum itself only appears inside of start right here. So sum inside of start right there. No.
What is the advantage of using a terminal instead of more production rules, is it possible to define what's the regular expression and say the production rules instead of the regular expression?
Yeah, it's a good question. The question is like, so we've made this distinction between there's the special terminal type of node and these standard production rule nodes, and what's the advantage of doing this, of having this distinction. And it is possible to not have that distinction, but what we're going to see in example 3 over here is what's called an interpreter for this tree, where we like actually go through then and do this computation, and the distinction will be useful at that point. At this point, the important thing here is that terminals correspond to leaves in the tree, and terminals don't have things like branches inside of them. You can't make different choices like this. You can't do a recursion inside of this. You can't have a child inside of a leaf node, and so the terminal is just a regular expression or is just a number, and does not have any of these like recursive definitions inside of it. Yeah.
It was like 1, 2, 3 asterisks forward, and there would be a branch at the product atom.
Yep. So there's a great question to be asking of like, okay, we've seen an example of 1, 2, 3 plus 4, and maybe I understand it, maybe I don't, but I can test my understanding by trying to create a modified example and seeing how that affects the corresponding tree. So I'm going to copy this modified example. The only difference between this modified example and the previous one is that we have a star here for multiplication instead of addition, and still in the grammar of, still in the language of arithmetic expressions. And recreate a new image like this, come back over here, reload this, this tree. And now we can see that, so the token over here goes over to Adam, the number, the terminal right here still goes straight to Adam, but then Adam goes to product, and product has the branching right here because the top atom over here gets connected to product directly. So the top atom going to product directly, this top branch up here like this, and then the bottom branch down here going product times atom. So we have a branch right here in the tree because there are 2 of these names in the production rule right here, and the star here gets consumed by that. And then everything is linear beyond that, going from product to sum to start, because we are choosing the, there's only one product for the sum and one sum for the start. So, yeah, good question. Did that answer your question? Yeah, Ron.
So, initially I was kind of confused whether you're using sum like in the product expression, but is it like because that enables us to use the tree to build it up?
You're saying sum in the product expression.
Or sorry, the other way around,
Product in the sum. Yeah, so why does like product inside of sum right here? Yeah, so this is going to be for enforcing order of operations, that we want like the multiplications to happen before additions. And so this particular structure is going to cause the multiplication to get grouped lower down in the tree than the additions. And so if we come down to this example right here that has addition and multiplication inside of it, and refresh that. Now there's, so addition and multiplication, each one of those corresponding to a branch over here. And the multiplication branch right here comes below the addition branch. And we'll see later on that will enforce order of operations for us. And then similarly, having the sum down here inside of parentheses, sort of having that even below, farther down in the rule set, is going to cause those parentheses to be closer to the leaves, helping for order of operations. So this lastmost example, relatively complicated expression right here, and run that, and it generates a relatively complicated tree for us here. Let's see. So this is the parse tree of these expressions. And the only difference here between example 1 and example 2 is it's the same, same grammar, but there's a handful of additional annotations inside of this grammar. And what these additional annotations do is they simplify our parse tree for us. So let's see. Let's move all of this together in one screen for a second. Maybe we can do it all like this. So on my terminal top right here, I'm going to open up example 2.py now instead of example 1. And we'll start with just the very first tree here again, like that, and draw that first tree and refresh it. And now instead of having a big long string of things, we just have the token number right here directly connected to start. What's happening is that, and let's do our example 1 again and compare this. So this is what our original tree looked like without these additional simplifying annotations. We had the atom and the product and the sum all contained together right here. If you have a question mark in Lark before a production rule, the question mark means that it will remove the rule from the parse tree if it only has one child. So sum here, product, atom, they only have one child. And so they're basically just noise in our parse tree. And so by putting the question marks in front of them, we can simplify things to get this simpler parse tree that doesn't have as much redundancy inside of it. And similarly, if we take, say, this more complicated one with a single addition, a single multiplication, draw that. Our parse tree now only has like the interesting parts inside of it, that like this atom here never appears because the atom doesn't really provide useful information to us. The next annotation that's happening up here, this arrow after an alternation, this renames the node in the parse tree so that you can determine which choice was made. So previously, when we had this rule right here, without the multiplication, it just said product between these two things. But this did not give us any way to say differentiate between a multiplication and a division. I'll illustrate that here, that if I comment out, so in Lark, in the Lark grammar, you can comment out portions using the hashtag syntax similar to Python. And if we have a, say like 1, 2, 3 divided by 4 times 5, run that, it's, it's still providing, it's because I modify, I'm in example 3 somehow over here. Example 2, modify that. Okay, sorry about that. So I've, in example 2 right here, focusing on what this portion is doing, commented out these two lines, generate this parse tree down here, and you can see it just says product and product. There's no differentiation between, we used a slash or a star over here. We just know that there was some sort of product rule happening. But this arrow notation allows us to provide names for each one of these alternate choices that is allowed to be made. And the resulting tree over here will tell us which one of these choices was made. So now it tells us that the division happened first, division happened between 123 and 4, and then the multiplication is happening after that. Nolan?
Are there any, do the question marks and arrows affect this parsing at runtime at all, or just for the visualization?
That's a good question. So there's no effect on the runtime at all. It's at this point, it's only affecting the visualization for us, but we'll see that this is an important transformation in order to actually be able to do the computation that this is asking. So it's partially cosmetic, partially semantic, but does not affect the runtime at all of anything.
It does not affect runtime, but does affect the computation.
I guess just hold this question until example 3. Yeah. Dan?
Honestly, like, there are a lot of like noises, like redundancy between like
Redundant.
like I'm thinking like you, the example one has like a lot of like tuning nodes stuff like that.
Right.
You said right now it's like more concrete noise.
Yeah, so like this atom term right here is just kind of noise in the tree because atom always comes directly above number. And adding, if we want to simplify the tree, like there might be some situation where we want atom always directly above the number, but if we don't want that, then putting a question mark in front of it allows us to remove it. Yeah. Let's see, all these questions they're good questions. They're really getting at what's like the final use case here that we're building up to. So we're going to jump straight to example 3 to be able to talk about that. Example 3 over here, the grammar is the same grammar as we looked at before. Actually, one last thing on example 2 that we should talk about. There's these 2 lines down here. They allow us to ignore white space. So you notice that I've been careful. All the examples I had, I did not have white space anywhere. This generates an error right now when we're in example 1. If you add white space, but with example 2, you're allowed to have this white space. And so this is a little bit of a syntactic sugar that a lot of Lark grammars will include in order to ignore white space. In whisper.cpp, there is nothing at all like this about ignoring white space, and white space does interact with language models in a slightly weird way based on how tokenization happens, and so some of their rules are written a little bit weird to handle white space. But the purpose of these lines for Lark for us so far is to ignore the white space. Okay, but example 3 here, the interesting thing, the reason we're talking about this is because we want to be able to, in this case, compute the semantics of this expression. This up here defines the syntax or the grammar of mathematical expressions, but we also want to actually be able to say, like, calculate what an expression is actually equal to. And usually, anytime we're defining a grammar, we want to somehow process the grammar, do something with it, do some sort of computation related to that grammar. And again, this calculator example is a very common, simple one because it's easy to understand what the computation that we might want to do right here is, that we just want to actually do 4 times 5 and divide that into 123. In Lark, the way that works is you create a class. Doesn't matter what the class's name is, but it has to derive from the transformer class right here. So calculate here is a subclass of transformer. And there's a handful of member functions inside of this subclass. And when we apply this class to the tree, what's going to happen is each one of these member functions will be applied to the appropriate node in the tree over here. So let's go ahead and load up our example over here. I have some print statements on here that are getting printed out up here. We can not think about those yet. I want us to look at this very simple tree first of all again and plot that, come down here. So this tree is just, again, the number 123. If we evaluate this tree somehow, we should just get the number 123. And the way to use Lark to evaluate one of these parse trees is whatever your class name is. So in this case, calculate. You'll do calculate.transform and then pass as the parameter the tree here. the name over here has to, so sorry, I was pausing for a second because I was expecting the output right here to be just the number 123, and I was getting this tree out. This print statement here, this function right here is not being run because this number is in all lowercase, and this number up here is as our terminal, so it's in all uppercase. And if I rename this to number like that, okay, I will do it by renaming this rule to be number like that, and define my tree 123, calculate the tree, and it gives me just the start rule now with 123. So the original tree here has this token number 123, token number 123. Lark, as it is processing this class right here, is applying each one of these rules. It applies this number rule to this number token right here, and one other rule that I should have had already written: start self comma xs is return xs of 0 dot value. So the tree is staying the same and calculating the tree. Oh man, sorry about that. I thought I had this in a good spot, but I must have messed up my committing or something. Anyway, we'll pause our discussion about this for a little bit, and we're going to go back to the README file here. Next week, when we'll talk about the homework that you'll actually have to implement. The homework that you'll be implementing will be writing some of these Lark grammars and writing corresponding calculate transformer functions down here, classes, and so we'll cover that in more detail next week. But the thing that I want us to see first of all, the stuff that's in here is stuff that we can, in the README here, stuff that we can talk about and how it relates to the large language model stuff in particular. So yeah, again, apologize that this example 3 I don't have something bad going on, but we'll cover that next week, covering the semantics of how to use these parse trees next week. And that will be important for this other homeworks. But parsing runtimes. So how long does it take to parse a context-free grammar? It turns out that there are 3 possible cases: an ambiguous case, an unambiguous case, and a deterministic case. There are 3 types of context-free grammars, and they each have these 3 different runtimes associated with them, either linear, n-squared, or n-cubed. We know that ambiguous grammars, so this runtime of n-cubed, we know that that is too slow for transformers to be able to implement. And so transformers, because they have the limit of n-squared, they can't implement every quadratic algorithm, but they can definitely not implement anything that is larger than quadratic. They will not be able to parse ambiguous grammars, and only these unambiguous and deterministic grammars. Deterministic grammars have a linear parsing time, and all programming languages are deterministic grammars. The calculator example that we've seen so far is a deterministic grammar. Other grammars that we will see are ambiguous and unambiguous. The deterministic grammar here, again, not related to there's a good question earlier about how these like question marks might affect runtimes of different things. It's not related to that. It's related to the actual structure of the grammar itself. And every programming language, every thing that people actually use in practice is a deterministic grammar. So Lark by default uses what's called the early algorithm. This is a guy's name from the 1970s. And the nice thing about Lark and this early algorithm is that it achieves the runtimes above without you having to know whether you have an ambiguous or an unambiguous or a deterministic grammar. So it can be useful to be able to differentiate these things, but you don't have to in order to be able to parse the grammar. Other grammars that are used in practice and programming languages or other parsers are, they have these sort of weird looking names like LALR or LL or SLR. They often have parentheses after them. If you ever see something like that, then the advantage of that is it has the guaranteed linear runtime. Disadvantage is a little bit harder to work with because you have to really understand the difference between the different types of grammars up here to be able to implement them. So let's see some more examples of context-free grammars. And again, all of these are going to be the deterministic context-free grammars. So RASP over here, this is their context-free grammar. It defines all of the statements inside of RASP, what you can and can't do. One of the things that we saw that was weird with RASP was certain statements required semicolons and other statements did not require semicolons. And in fact, you were not allowed to have a semicolon. And they have this distinction between a statement for the RASP language and a statement just for their REPL. The REPL does not require the semicolon, not allowed. The RASP statements do require these semicolons. So yeah, again, when I was first learning the RASP language, none of this is like in their paper or their documentation about things. This is the documentation of what is a valid RASP program right here, this grammar. JSON also has a corresponding grammar associated with it. There's this concept of an RFC. It's a request for comments. Anytime somebody is proposing like a new standard, they create one of these requests for comments at this organization, the IETF, that tracks them all. And this is where standards are published. This is what the official standards for different things look like. Let's see. So here's the JSON one, the JSON grammar being defined right here. URLs also have a corresponding grammar associated with them. Here's the grammar for URLs. URLs happen to be a regular language, and so this giant grammar that is like 2 pages long right here could be replaced with just this one-line regular expression right here. But yeah, nobody can read what's going on with here, like seeing if there's a typo or not. And so these, even in regular expressions, regular languages, people like to use these grammars because they're just easier to try to figure out what's going on. So yes, URLs, SQLite, their grammar is defined right here. So this is the, you're using SQLite before. Here's the full definition of all these possible statements that can be defined in SQLite. Their documentation uses what's called railroad diagrams to visualize these grammars. But there's just like a one-to-one mapping from this EBNF format right here, the grammar format, to these railroad diagrams. Their actual definition right here is a very long definition. This is their parser code right here, their grammar. Doing a lot of like weird optimizations inside of it to make sure that it is a deterministic grammar. But the EBNF form right here, this is the simple thing to look at. So again, yeah, implementations here. For me, when I first saw like ChatGPT writing code, I was very surprised about that because, well, one of the things we talked about before was that snowball effect of if you're writing like a program, you can't have a typo like anywhere in the program. A minor typo can cause your syntax errors, cause things to not parse, and so the code won't even run. And if you just have even a very, very high probability, like 99.99% of getting the next token correct, multiplying that together 1,000 times gives you a low probability that the overall program is correct. That was the paper that we went over in class, talked about that snowball effect. So I was very surprised that ChatGPT was able to actually output syntactically correct programs. But in retrospect, it's not surprising to me because programming languages parse in linear time. They are these deterministic grammars that take linear time to parse. And LLMs can compute not everything that's quadratic, but some things that are quadratic. I suspect probably everything that's linear, but I don't know that for sure. But this is definitely smaller than this, so it makes sense that an LLM could possibly compute this thing over here. So it seems very reasonable to me that LLMs can write grammatical code. Surprising to me at first, but now seems like a very reasonable thing. Another thing that a handful of people have asked me about is LMQL. How does that compare to the context-free grammar stuff over here? In their documentation, LLMQL specifically says that they are equivalent to these context-free languages. They can do whatever a context-free grammar can do, and they cannot do anything that a context-free grammar cannot do. So some useful examples of like what is outside the realm of possibility for non-context-free languages, like what can you not do with a grammar? What can you not do with Lark? Here's one of the prototypical examples. This is the sort of formal definition here where you have two strings W that are repeated. So the string like A, B, C, D, E, F, G followed by A, B, C, D, E, F, G, exactly the same thing. This seems like a very simple thing to do, but you cannot describe that with a context-free grammar. So if you need your output of a LLM to do something like this, you cannot do that with LMQL. You cannot have whisper.cpp or llama.cpp enforce output like this. What you can do is you could have it enforce output where the second string is reversed. This up caret r raised to the r power is a notation for reversal of the string. So you could do A, B, C, D, F, G, then G, F, E, D, C, B, A. That is a reasonable context-free grammar, but without the reversal, it's not context-free. Another thing that is not context-free is if we have like A to the B, A to the N, B to the N, C to the N, where A, B, and C are all symbols. That's not context-free. We saw that A to the N, B to the N, that by itself would be context-free. But if you have to count more than just like two symbols, how many they are, that is no longer context-free anymore. Anytime you're like counting more than one thing, then you're definitely not context-free anymore. Anything that requires like complex computation somehow, where this is like, again, very loosely defined, but that's probably not context-free. So like the set of prime numbers, that's not context-free. There is no grammar that you can write that gives you that only matches the set of context numbers or the set of prime numbers. Yeah, again, we're speed running this, so we're not like showing how to prove these different things, but these are like some useful intuitions about what can large language models possibly do or not do. They're never going to be able to, well, maybe never is too strong of a word, but if they can't do non-context-free languages, then it's not going to be able to do these types of things right here. Turns out actually that Python is almost context-free, but it is not context-free. The problem is that white space and indentation for code blocks, so the being white space sensitive, that is not context-free. That's what's called context sensitive. And the reason all programming languages before Python were not white space sensitive is because nobody knew how to write one of these parsers that would handle white space sensitivity. One of the innovations of Guido was doing like a pre-processing pass that handled just the white space stuff, converting it into indent and detent tokens, and then using a standard LL1 parser. Lark is able to do this. It has documentation here if you wanted to do this. So Lark can do things that are not context-free, but only in a limited sense. And Python here, if you want to look at their their grammar, their documentation, this is something that I do on a moderate basis if I'm confused about some weird syntax and what's allowed and not allowed. This is where it's actually formally defined. And one, I don't know, sort of cool fact is that, so Guido von Rossum, no longer the benevolent dictator for life, He stepped down in 2019. The reason he stepped down was because he was fed up with this LL1 parsing in Python and thought that he didn't have enough time to dedicate to improving the parsing in Python as the benevolent dictator in charge of all sorts of like social things going on in Python. And so he stepped down in order to change parsing from this LL1 algorithm into this other algorithm called PEG. And here this PEP 617 describes like exactly why that's useful, and it talks about like the context-free grammars in Python and why they made the decisions that they made. Yeah, so that's high-level background stuff. Next time in class, we'll go over more of the technical stuff, fixing this example stuff, and then what to do for this next set of homeworks. Any questions about any of this high-level stuff?
Where should we
Sure.
get the like first?
I need to create a thing on Sakai, don't I? Yeah, I will do that hopefully today. If it's not done today, then make an issue on GitHub and that'll remind me. Yeah. Well,
You did outside of the.
That's fine.
For next week, but for the reversing, for the thing where reversing it is possible, but just repeating it is not.
Yeah.
You just like reverse it twice.
That turns out not to be context free. Yeah. So, yeah. I don't have anything else to say that's not like too complicated for where we're at.
Yeah.
Okay, if other people have other questions, I'll stick around after class to get those answered. Otherwise, I hope you have a great week. I'll have office hours on Friday like normal if you want to chat about anything. Otherwise, see you next week.